All right, so now we know discrete logarithm problem. We've seen the example of key exchange as the Diffie-Hellman key exchange. We also seen an encryption algorithm based on a discrete logarithm problem called el-gamal. Now it is good time to move on to different types of algorithms. So we talk about three things, and we have seen examples for two. So for encryption, we have seen an example. For key exchange, we have seen an example. And now it is a good time to see a solution for digital signatures. So this is for authentication. So first, let's give the main definition. Then I will talk about digital signature algorithm, DSA, or digital signature standard. So both abbreviations are correct. A digital signature is a number dependent on some secret known only to the signer's private key, actually. And additionally, on the contents of the message being signed. So that is the idea. You sign a message based on your secret information. So this way you prove that only you could sign it that way. Due to the size of the signatures, hash of the message is signed instead of the message itself. This is very important. People think that you are signing the whole message, but think about the, for instance, NVIDIA display driver. Currently, it is hundreds of megabytes, sometimes gigabytes. So if you sign that driver, the result will be, again, hundreds of megabytes or gigabytes. So you cannot sign all of these things. Instead, you simply take the hash of the input. The result is very simple. Like if you use SHA-256, the result is 256 bits. You sign that instead. So this is why digital signatures are not actually encryption algorithms, because you're not encrypting anything. This is also important. Some people think that hash functions and digital signatures are encryption algorithms, but they are not. This is a huge misconception. Signatures must be verifiable. If a dispute arises as to whether an entity signed the document, an unbiased third party should be able to resolve the matter equitably without requiring access to the signer's private key. So this is the main idea behind digital signatures. Disputes may arise when a signer tries to repudiate a signature it did create. So you sign something, then you deny it. Or a forger makes a fraudulent claim, saying that you signed something, but you didn't. Okay, so a digital signature should be able to, destroy these disputes if it is a good algorithm. Digital signature schemes can be used to provide the following basic cryptographic services: data integrity, the assurance that data has not been altered by unauthorized or unknown means; data origin authentication, the assurance that the source of data is as claimed; non-repudiation, the assurance that an entity cannot deny previous actions or commitments. These are good properties, right? Again, as the misconception, a lot of people think that a digital signature is an encryption algorithm, but digital signature algorithms are not encryption algorithms, okay? Both are focused on different things. Encryption algorithms focus on confidentiality. Here, as you can see, we focus mostly on data origin authentication, data integrity, or non-repudiation. Digital signature schemes are commonly used as primitives in cryptographic protocols that provide other services, including entity authentication. There are some standards for them, but most of them are old. Authenticated key transport. Here are some, again, ISO, ANSI, and other standards. And authenticated key agreement. You can see related references here. So let's focus on the digital signature algorithm or standard, so DSA or DSS. The DSA was proposed in August 1991 by the US National Institute of Standards and Technology. It was specified in the US Government Federal Information Processing Standard, FIPS 186, called the Digital Signature Standard, DSS. The DSA can be viewed as a variant of the el-gamal signature scheme. Its security is based on the interactability of the discrete logarithm problem in prime order subgroups of ZP star. But importantly, it looks like the people are moving away from digital signature algorithm. So when I looked at the current draft version of FIPS 186-5, which is the most current version of this standard, I took this following quotation, which says, prior versions of this standard specified the DSA. This standard no longer approves DSA for digital signature generation. DSA may be used to verify signatures generated prior to the implementation date of the standard. See FIPS 186-4 for the specifications for DSA. It looks like people are, by people I mean NIST, are moving away from digital signature algorithms. But in the same document, you will see elliptic curve digital signature algorithm. Okay. So, you know, same thing also applies for RSA. People are starting to move away from RSA, but, you know, probably they will be around for some time. Let's look at how the digital signature algorithm works. We start with parameter generation because first we need the group, right, ZP star. So we should choose the number P and so on. So start with choosing a good hash function. So if you need, for instance, 256-bit output, in other words, 128-bit security, you should choose SHA-2 or SHA-3 and so on. So you first specify which hash function you are going to use. Because as I told you before, we never sign the message itself, we sign the hash of it. Then you choose key lengths, L and N, for example, 3072-bit and 256-bit. Due to previous slides, now you can understand where these numbers are coming from. This will be our group size. You know, this will be our kind of a key length. Choose n-bit prime Q. Choose L-bit prime modulus P such that P minus 1 is a multiple of Q. Okay, so we are working on two different groups. Choose G, its multiplicative group order modulo P must be Q. Okay, so G is an element and it generates a group. Its order must be Q modulo P. So now we have parameters P, Q, and G. And you can give these numbers to maybe the only one person you want to communicate, or either you choose it once and for all, and everybody in the system can use these numbers, okay? This is for parameter generation. So in the elliptic curve scenario, here we will be talking about choosing an elliptic curve. For instance, in the case of Bitcoin, Satoshi chooses a elliptic curve. So all of the people who create the Bitcoin account actually uses that same elliptic curve. Similar thing can apply here. You can choose parameters for one system, and everybody can use these parameters, which actually determines your domain. Okay, so this is initialization phase. This is valid for everybody. Now, for the user, you have to generate your own secret key. What you do is as follows: randomly choose a secret key X, where X is between 0 and Q. Recall that Q is an n-bit prime, and here is 256, for example. This is why your secret key is 256-bit if you choose these parameters, but your group size P will be 3072 bits due to sub-exponential time algorithms for discrete logarithm problem. As in the case of el-gamal, you see that I calculate the x power of G modulo P and obtain Y. So this will be my public key. This will be my private key. As simple as that. So I'm actually using el-gamal, but not for encryption, for digital signatures. So signing works as follows. Anytime you want to sign a message, you have to randomly choose a K between these values, and you should never use the same number again. This should be also kept secret, okay? If you publicly announce it, then your secret key leaks. This is important. So for the signing, for that message, you randomly chose a value K. You calculate the K power of G modulo P, then modulo Q, which returns the value R. Then you also calculate S, and S is calculated as follows. You take the hash of your message, edit the value X and R. X was your private key. R is the value obtained here. Okay. Multiplied with K inverse and calculated modulo Q. Okay. So your signature actually now is these two values, R and S. Okay. You sign the message. Of course, when you want to prove it, you also give them the message saying that I signed this and this is the signature. So when they want to verify it, what they do is as follows. They calculate first S inverse modulo Q. So they receive S from you. They calculate W. They also calculate U1, which is hash of the message multiplied with this W value. Then you also calculate R times W, you obtain U2. Then you calculate V, which is G to the power U1 multiplied Y to the power U2, which are the values you calculated here, modulo P, modulo Q. Now, if V equals to this R, then the signature is valid. If it is not, then the signature is not valid. So you might think that why this works. Actually, the same thing applies as in the previous lectures. Here, we are calculating V equals to this value. Just instead of U1, write this part, for U2, write this part, take these values, come here, and you will realize that R is the same thing with this V if you calculate everything correct, if the signature is correct, okay? It is not that hard to prove it. So it comes from actually basic number theory, okay? So this is as simple as that. So if you want to look at the whole procedure again, we first choose some parameters. For instance, if the security in the future, if you want more security, for instance, instead of 128-bit security, maybe you want 256-bit security. So here you choose 512 bits, okay? For instance, SHA-2, so SHA-2 with 512 bits. But your group size now has to be 15,000 something, okay? So you choose these parameters again. Then you choose your secret key accordingly. In this signing phase, you do these operations, and the verifying case, this is what you do. So this is actually what happens when somebody sends cryptocurrency to somebody else. Actually, you are signing that message, okay? And everybody checks that you really own that money and send it to somebody else, okay? So let's focus on the security of this algorithm. The security of DSA relies on two different discrete logarithm problems, actually. One is the discrete logarithm problem in ZP star, where the number field sieve algorithm applies. This algorithm has a sub-exponential running time. And more precisely, the expected running time of the algorithm is given as this, okay? Where C is this number. So it is not exponential, but sub-exponential. This is why P has to be somewhat large, because we have a sub-exponential time algorithm. The second discrete logarithm works to the base G in the subgroup of order Q in ZP star. Given P, Q, and G and Y, find X such that Y is equal to G to the X modulo P. For large P, for instance, 3072 bits, the best algorithm known for this problem is Pollar's row method and takes about this many times, okay? Due to this square root operation, this is why we choose Q as 256 bits, okay? Because Q will be 2 to the 256, and due to the square root, the security will be equal to 128 bits, okay? Actually, Pollard's row algorithm forces us to choose here 2 times 128-bit when you need 128-bit security, okay? And here you are choosing 3000 bits due to number field sieve method, which is sub-exponential, okay? These numbers are coming from it. This is very important because a lot of people doesn't know this. We still see papers, academic papers published where they focus on publications earlier than 2000, and they choose this group size sometimes 1024 bits, thinking like RSA 1024 is secure, okay? Even in the el-gamal or digital signatures, they take this value as 1024, which is not acceptable in today's technology, because if you choose it like this, this would mean that you provide 80-bit security. And 80-bit security can be broken by agencies or, people coming together on the internet or botnets and so on. So this is why this is the smallest values you can take today. If you want 128-bit security, you have to choose your group size as this, again, and the key space as this, okay? But in the case of elliptic curves, we will get rid of this part because number field sieve here This part will not apply for elliptic curves. This is why we can get rid of these huge group sizes and we can work on something small like 256 bits.